Nuclear energy. It's a prevalent and potent resource in modern-day history, for better or worse. Its remarkable power is astonishing, and the only way to learn more about it is to understand its roots. The word nuclear is derived from the word nucleus, and this is where everything begins. By taking a closer look, it is possible to see that the basic atom is comprised of a stable configuration which consists of an equal number of protons to electrons. The number of neutrons varies per atoms of each element. Atoms of an element with the same number of protons and electrons but a different number of neutrons are named isotopes. Many isotopes tend to be stable, however, there are exceptions. These would be radioisotopes or radionuclides. These unstable isotopes have the tendency to disintegrate over time, dispersing excess energy through alpha and beta particles and gamma waves. As they decay, they release varying amounts of energy, and each species decays at a different half-life rate. Half-life is the time it takes for one-half of the radioactive material's atoms to decompose. This is exactly what causes radiation, since radioactive material is something which decays over time, releasing energy as it breaks apart. The amount of energy found within the nucleus is tremendous, and so if the atom is in an unstable state, it has the potential to emit a lot of radiation. That's why radioactive compounds must be handled with extreme care, or they can lead to other terrible disasters, such as the Chernobyl nuclear power plant. However, radioisotopes are also very helpful to us when used correctly, and technetium-99m is a great example of it. It's a species that is very commonly used in many medical diagnostics procedures. It is a type of radiopharmaceutical which includes a number of radioactive drugs used for diagnostics procedures with therapy. Some radioactive substances change form to create another substance which is more stable. This is named a transmutation, and it is the basis for how technetium-99m is produced. Technetium-99m is formed from a combination of two chemical reactions. First, neutron activation occurs from molybdenum-98. Neutron activation is a method where materials are induced to become radioactive. It occurs when the material absorbs a neutron into its nucleus. This causes molybdenum-98 to transmute into molybdenum-99. Molybdenum-99 then decomposes into technetium-99m, releasing beta particles as it does so, since it is still an unstable radionuclide. Beta particles are equivalent to high-speed electrons which dissipate from a decaying radioisotope. When radioactive species emit beta particles, the original radioisotope ejects an electron. This is because there are too many protons or neutrons. The neutron either decays into an electron and proton in beta minus decay, or a proton decays into an electron and neutron in beta plus decay. It then decomposes into a radioisotope plus the beta particle. As this occurs for technetium-99m, the radioactive material enters an excited state named the metastable state. This is a state in which the chemical substance is excited for a prolonged period of time, and the M in technetium-99m is indicative of this state. Then, finally, technetium-99m decomposes and dissipates, releasing gamma waves as it does so. Gamma rays have no mass or electrical charge. They sometimes behave like particles due to the energy that they have, and other times like waves which fall under the electromagnetic spectrum. That is referred to as wave-particle duality. This occurs since they're comprised of photons which are both naturally magnetic and electric. Simply put, gamma rays are a form of electromagnetic radiation which includes types of energy found circling throughout space. Gamma rays have some of the shortest wavelengths of the waves from the electromagnetic spectrum, meaning that their photons have a very high amount of energy. Therefore, they must be handled with great care. Gamma rays are very safe when released in small quantities as they are by technetium-99m. This radioactive species has a half-life of 6.02 hours, making it perfect for medicinal purposes. It can be harmlessly injected into the human body in small doses, or even ingested in the form of a food or fluid. There, it works with the gamma camera to be detected. The gamma camera uses a crystal that glows in the presence of gamma rays. The intensity of the light it illuminates is measured using light sensors, which convert the readings into a numerical value that doctors can analyze. As the radioactive tracer moves throughout the body, it releases gamma radiation. The gamma camera can therefore create a detailed map of the human body, highlighting its functions. Cells even absorb this radioactive material, showing spots where there is an increase in the amount of cell division. This can provide further insight onto developing medical problems such as a tumor. There are different compounds that technetium-99m can be combined with in order to study other organs. For example, technetium-99m sodium pertechnetate can be used for scanning the brain and thyroid. It is able to bond with these other compounds due to its many oxidation states. Despite all the benefits of these substances, they cause many problems for humans as well. All radioactive material is extremely harmful when exposed to living organisms, since it has the potential to destroy their cells. Therefore, it must be disposed in some way. However, current methods are not providing a reliable solution. The two most common methods include direct disposal and reprocessing of the nuclear waste. Direct or geological disposal is burying the radioactive material deep within the earth, typically 300 meters or deeper. This method is very expensive, and the long-term structural stability and environmental effects of such repositories are still unknown. There could be some unprecedented seismic activity near the planet, compromising its safety, or possibly some other long-term problems which no one has thought of, or more precisely, problems that no one can even predict, since this waste requires hundreds to thousands of years to decompose, to the point where it is safe to dispose of. Moving on to reprocessing, it is commonly only applied to used nuclear reactor fuel. It is mostly only the uranium that is reusable, and so not all intermediate to high-level waste can be recycled. Also, take into account that there will always be some used fuel left over, and so we go back to square one, which isn't to permanently get rid of the waste, but to simply store it elsewhere until it's safe to use. Both of these methods seem sustainable in the short term, but there can always be problems with planning such complex facilities that we won't be aware of until it's too late. A solution to this problem must be found, since our world depends on the use of nuclear energy. Please raise awareness of this topic to all the scientists, engineers, environmentalists, and other great minds of the world. Spread the word and inspire change, since the sooner that this problem can be solved, the better it will be for our future.